This video covers topic number 10, solving absolute value inequalities. We're going to solve absolute value inequalities and verify them using a graphical tool. Now, back in Algebra 1, we had talked about inequalities. We had open and solid dots coming from greater than and less than, solid dots coming from greater than or equal to, less than or equal to. And we covered two different types. We talked about ands and ors. So putting the dots on both of these compound inequalities, and or sometimes called disjoint, we remember that and compound inequalities, they shaded towards each other, so our solutions were stuck between the two values. And for or compound inequalities, our solutions were facing away from each other. We shaded the regions going in opposite directions. And meant the arrows were going towards each other, and or meant the arrows were going in opposite directions. Additionally, when we graphed linear inequalities, we again used solid and dotted lines, and as well as shading above and below. So here, if I'm graphing this, y is less than 2x minus 3, we started out just graphing as if it was a line, started negative 3y intercept, up 2 over 1, up 2 over 1, up 2 over 1, or the slope. We're going to use the dash line in this particular case. And since we have y is less than, we're going to be shading below the graph, where y is below the graph. And we get our linear inequality. Now, combining these two ideas, we can go ahead and apply this to absolute value, solving absolute value inequalities. Much like in Algebra 1, and compound are still going to exist. They're actually going to be relatively easily identifiable, so long as we've isolated the absolute value bars. So, I know that I have an and compound inequality when we have a less than inequality. It doesn't need to be, it could be less than or equal to. And we know that we have a or compound inequality when we have a great or symbol. So whether it's greater or great or equal to, we have these compound inequalities. In this case, we're going to have a disjoint. This one would be and. Meaning with less than, if I have absolute value less than or equal to, our solution should be facing each other, should be stuck between two regions. If the absolute value is greater or equal to, we should have an or, and the solution should be facing out. Now, with graphing absolute value inequalities, we're still going to go ahead and approach like we did yesterday, graphing the left and the right side separately. Here our left side is an absolute value function, and the right side is a horizontal line at y is equal to 1. However, we're not always going to use solid dots. We still need to pay attention to whether it's solid versus a dotted line. In this case, we have a greater than symbol, so that means that we'll have a dotted line on both. Now, in terms of regions that we are going to shade, we're going to shade where the absolute value is either above or the absolute value is below the graph. So in this particular case, we're looking for where the absolute value is above our other function. So in this particular case, we're looking where is the V shape above our other graph. Well, if we're going to go ahead and look at this, we see here is our V shape. It is above our other line on the very tips and the very edges. It is above our other graph. Okay, well, what regions does this include? Well, that's what we'll be figuring out when we solve. So let's go ahead and take a look at this. Let's dive into this a little bit more graphically. So here we're going to go ahead and solve this inequality graphically. We're going to graph each side of the inequality separately and then worry about our type of line and shaded regions. So we look immediately at our inequality symbol. It's less than or equal to, which means we're going to have solid lines on both functions. So using either Desmos or our graphing idea, we're going to graph the left-hand side and the right-hand side, and we have our two functions. Now, in terms of the inequality, we have, again, less than or equal to. So in this particular case, our absolute value needs to be less than or equal to. Less than or equal to, the absolute value needs to be less, which means that if it is less, we are looking for where the absolute value is below our other function. So looking at these two graphs, where is the absolute value the bottom function? Where is it actually below? Well, we could see it is this region of the graph is where we are below our other function. It is the bottommost function. Well, between which two values is that? Well, starting at x equals -5 and ending at x is equal to 1 and all the x values in between, we have where our bottom function, the absolute value, is below the linear function. So that would make me think then that our solution is going to be between -5 and 1. Well, let's go ahead and justify this in terms of an algebraic approach. You'll notice that our steps are very similar to what we were doing with absolute value equations in terms of we're going to isolate the absolute value bars, think about the relationship to see whether we have any special solutions, no solutions, infinite solutions, extraneous solutions. And then we're going to go ahead and, if we don't have one of those special relationships, rewrite as 2, go ahead and do the split, and then solve. And go ahead and make sure we check our answer. One additional step on the end is we're going to go ahead and provide a graph on the number line. So let's start off by isolating the absolute value by subtracting 1 from each side. Now that the absolute value bars are isolated, let's think about this. The absolute value is less than or equal to 3. Nothing crazy going on here. We're looking for negative relationships here, no negative number. So we're going to go ahead and perform the split. Now remember, when we perform the split, we write as 2 separate inequalities. One, the positive case where it stays the same, and one where we make the right-hand side negative. Now, with an inequality, we have to add one additional step. We need to go ahead and flip the inequality symbol. So notice here it was less than or equal to. It now became greater than or equal to, along with that negative 3. So from here, we're going to solve both sides, giving us x is less than or equal to 1, and x is greater than or equal to negative 5. Now, we didn't talk about whether this was an and or an or compound inequality or disjoint inequality at the beginning. And or. It's helpful when we start solving, but it's okay if we forget, because as long as we do our inequality correct, when we go back and check, it should match up. So this is a less than and, so this in fact was an and compound inequality, meaning that our solution should point towards each other. Well, if we come down here on the number line and put a value of 1 with a solid dot, because we have or equal to, and we're shading 2 values that are less than 1, so that would be 0 as opposed to 2. And we come over here and put negative 5 with a solid dot, and we shade 2 values of x that are greater, so compared to negative 4 and negative 6, we'd be shading towards negative 4. Hey, we get our values that bounce in between the negative 5 and positive 1. Again, similarly, this should match up to what we see in terms of a graph on our inequality. The absolute value was below the horizontal line of 4 between the values of negative 5 and 1, and we also got it when we did our algebraic approach. Let's take a look at a few more examples. Starting with example A, let's focus on the graphical approach. We have to use dotted lines in this case since the inequality is greater than. Take a moment and graph these. We get our 2 functions. Now in this case we're looking for greater than, so we're looking for where is the absolute value greater, or where is it above our other function? Well, the absolute value is the highest function here and here. It is above our horizontal line in those particular spots. Well, what x values does that correspond? Well, our intersection occurs at negative 1 and negative 5, and it must occur outside of those regions, going towards negative infinity and going up towards positive infinity. So it looks like we have an or disjoint inequality in this answer. Let's go ahead and solve it algebraically to back this up. Starting off by isolating the absolute value bar, noticing that we don't have any negative number relationships here, we're going to go ahead and do the split. Notice it again that on the negative case, we are flipping the inequality along with making the number negative. Going in and solving both of these, we get x is greater than negative 1 and x is less than negative 5. Thinking about whether this is an and or an or compound or disjoint inequality. Great or, it's going to be an or compound inequality. So when we put these on the number line, we're going to put a dot at negative 1 along with an open dot. If I'm shading for values that are greater than negative 1, 0, or negative 2, we're going to shade towards 0. If I put an open dot on negative 5, if we're shading towards values that are less, negative 4, negative 6, we'll shade towards negative 6, and we get our inequalities. Matches up what we see happening graphically, where the absolute value is above our line in the outer regions, pointing towards negative infinity and positive infinity. Okay, let's take a look at example B. Graphically, we'll go ahead looking at the 2 graphs, our absolute value function, vertex at 3, 2, and our horizontal line at y equals negative 4. Looking at and interpreting the absolute value, here we have the absolute value is less than the horizontal line. So where is it below our horizontal line? Where is our absolute value function below the horizontal line? Well, if you're wondering and thinking about this, it's never below. Therefore, we have an answer of no solution. Well, what does this look like when we start to solve it algebraically? Well, we're going to go ahead and try to isolate the absolute value bars first, giving us the absolute value is less than -6. Now, thinking about the relationships between absolute values and negative numbers, we have this particular scenario. Now, we know from before, we know that an absolute value cannot equal a negative number. But we're not dealing with equal sign here, we're dealing with a less than symbol. So the question is, if an absolute value cannot be equal to a negative number, so it also cannot be less than a negative number. So in this case, we algebraically get no solution for our answers. Okay? Similar reason is what we used before, but we need to go one step further. Since we're not just talking about it being equal, we have to talk about whether, since it cannot be less, it can't be equal to, so it can't definitely not be less than a negative number. Okay, last example, let's approach this one graphically, same idea. Here's our graphical approach. Now, in terms of the absolute value, we are looking for where is the absolute value greater than or equal to. Well, if greater than or equal to translates to where is the absolute value above our other function. So where is this v above our horizontal line? It's always above. So if it's always above, that means we have all real numbers as our solution. It's always, every x value we could think of makes this inequality true. So what does that look like in terms of the algebraic approach? We'll start by isolating the absolute value bar, giving us the absolute value is greater than or equal to a -2. So now we need to think about the relationship between absolute values and negative numbers. So from before, we remember that an absolute value cannot equal a negative number. Well, we don't have an equal sign here. We have a greater than or equal to symbol. So if it can't be equal to a negative number, it must mean that it has to be positive. So it's always going to be greater than a negative number. Every positive number is always greater than a negative number. So in this case, we would say all real solutions. All real solutions. Once again, this explanation is essential for us to go ahead so we can jump to our final answer. Much like above, we can't just say no solution without an explanation. We must say, well, it can't be equal to a negative number, so it also cannot be less than a negative number, leading us to the answer of no solution. Just like here, absolute value can't be negative, equal to a negative, so it must always be greater than a negative, meaning that it's all real solutions. Okay, these two explanations go along with our two answers. We see it on the graph in both of these cases, and we see what happens algebraically. So, there it is in terms of solving absolute value inequalities. We have possible choices of all real solutions, no solutions. We have or compound or disjoint inequalities is what they're called, where the answers are, the solution regions are pointing away from each other. And we have solutions regions where we have an and, where our solution regions are pointing towards each other. We're between two values.